What's up, guys? So today we are going to introduce a couple of new functional groups. We're going to talk about acetals and hemiacetals. So a hemiacetal is the product of an addition reaction between an alcohol and an aldehyde or ketone. This is a reversible reaction that requires acidic conditions. So this molecule on the right is what a hemiacetal looks like. So a hemiacetal is going to have a central carbon that is attached to both an OH group and an OC group. And we're going to call that central carbon our hemiacetal carbon. So when you're trying to identify a hemiacetal, look for that carbon. So look for this 5-atom sequence, HOCOC. And so just a little bit of caution here. This COC part is not an ether. These do not behave like ethers. They have radically different chemistry and functions than ethers do. So treat a hemiacetal as its own separate functional group. So these hemiacetals that we produced in the previous reaction we were talking about tend to be unstable, and if there's excess alcohol, it's going to continue reacting and form an acetal. So an acetal is the product of a substitution reaction between an alcohol and a hemiacetal. And so just like before, we're going to look for that central carbon, and that central carbon is going to be attached to two OC groups. So when you're trying to identify an acetal, look for the COCOC linkage. And that central C is going to be your acetal carbon. And just like I warned you on the previous slide, these are not ethers. They have radically different chemistry than ethers, even though both functional groups have an oxygen sandwiched between two carbons. Okay, so I think the best way to learn this reaction is to just jump right in, and let's try an example together. So I want you to start by pausing this video and just giving me a name for both of our reactants. Okay, so our first reactant, our carbonyl, is a ketone with 3 carbons, so that molecule is propanone. And our second reactant, a 3-carbon alcohol with the OH attached at one of the terminal carbons, is 1-propanol. So while the full mechanism of this reaction is a bit outside the scope of this class, we can do a simplified version here. So we're going to treat this reaction just like any other addition reaction that we've already done this semester. So I'm talking about reactions like hydration or hydrohalogenation, where we're going to split a molecule and add it across a double bond. So in this case, we're going to split our alcohol between the oxygen and the hydrogen, and we're going to add that across our double bond. So let's start by breaking our double bond on our ketone. And we're going to add the hydrogen from our alcohol to our previously double bonded oxygen. And we're going to add the rest of our alcohol to our previously double bonded carbon. And there is our hemiacetal product. Okay, so let's point to the hemiacetal carbon now. So we're going to look for that HOCOC linkage, and that central carbon is going to be our hemiacetal carbon. Okay, so like I said, these reaction products tend to be unstable, and if we have excess alcohol, the reaction will continue. So here we have our hemiacetal from the last slide, and the same alcohol that we used to form it, and this reaction is going to work like a double replacement reaction, where the OH from our hemiacetal and the H from our hydroxy group on our alcohol are going to join together to form water, and everything left is going to join together to form an acetal. Okay, so this time we're going to identify our acetal carbon by looking for the COCOC linkage. So that means our central carbon in that COCOC linkage is the acetal carbon. Okay, now that you have a brief crash course into hemiacetal and acetal synthesis, let's see if you can do an example on your own. So go ahead and pause this video, give me a name for the reactants, draw the hemiacetal product, and point to the hemiacetal carbon. Okay, let's see what you came up with. So our carbonyl reactant is a aldehyde with a methyl substituent at position 2, So this would be 2-methyl-propanol. And our alcohol has 6 carbons in a ring, so this would be cyclohexanol. So we're going to split our alcohol between the oxygen and the hydrogen, and then we're going to break the double bond on our carbonyl. We're going to add the H from our alcohol to our previously double bonded oxygen, and the rest of our alcohol to the previously double bonded carbon. So your final hemiacetal product should look similar to that. Okay, now let's find our hemiacetal carbon. So we're going to look for the HOCOC linkage, and that central carbon will be our hemiacetal carbon. Okay, let's keep this reaction going. So like I said, these hemiacetals tend to be unstable, and if we have excess alcohol, the reaction is going to keep going. So go ahead and pause this video, see if you can draw the final acetal product for this reaction, and point to the acetal carbon. Okay, so the first thing we're going to do is form water with the hydrogen from the hydroxy group on our alcohol and the OH group on our hemiacetal. And then we're just going to connect everything else together to form our acetal. So here is our alcohol residue attached to our hemiacetal residue. So your final acetal product should look something similar to that, but hopefully a little bit better. Okay, so last thing for today, let's point to the acetal carbon. So you're going to look for the COCOC linkage, and that central carbon will be your acetal carbon.